Okay, so hello and welcome again. So last time we had discussed on this problem of platform having three rods supporting it, and then there is a change in temperature wherein aluminum had caused this one to be this aluminum had caused the pushing of this platform that is resting on the copper. So today I'll just have another variation on this problem wherein we might ask at what temperature will the copper will have no stress. Okay, at what temperature will the copper rod will have no stress if the mass of the platform is equal to 100 kilograms. Okay, so what is the scenario now? Of course, if there will be an elongation on this rods, okay, so from the problem, this platform will no longer be assumed to have no mass. Okay, so meaning we will now consider a weight equivalent to 100 kilograms, or this is actually a mass equal to 100 kilograms. So therefore, there will be an initial deformation, say if we do not have any change in temperature yet. If there will be a mass here, say 100 kilograms, therefore there will be a corresponding deformation on our rods, particularly on the outer rods, the copper. Okay, why? Because 100 kilograms is being absorbed by the copper rod. So we would like to investigate what is the extent of the deformation of the copper, granting that there will be a 100 kilogram mass here. So of course, by free body diagram, okay, by FBD, we can just say that this is PCU, or 2 PCU, that is carrying the 100 kilogram mass there. And then for that, and it's obvious therefore that this PCU is equivalent to just half of this mass because of symmetry. So both are carrying 50 kilogram mass. So from that, we can now conclude that PCU is 50 times 9.81. That is equivalent to 490.5 Newton. Okay? So 490.5 Newton. So from this, we can now compute for the deformation caused by this loading. First, this is for copper. PL over AE of the copper, we have 490.5 times the length, which is 750, times the area for copper is 500 millimeters squared, and a 120,000 modulus of elasticity. So therefore, we will have stress in the copper or deformation in the copper equivalent to 0.00613 millimeters. So this is actually just a hairline of deformation caused by these 100 kilograms. So if we're gonna set that the copper will have no stress, of course we will let a elongation an elongation for the aluminum exceeding this deformation. So if we're going to illustrate that one, say I'm gonna let all of this to be elongating with a certain increase in temperature. Okay, say this is our platform. So this is elongating, okay, and that is elongating also at a certain extent. Of course, we do not know that extent. And then of course, this one here will elongate so that it will have a level, an equal level with that of the copper. So if we're going to label that, this is the 0.18, this is the deformation of T due to T of the copper, and then this is the deformation C. So this shall be aluminum. So if this will be the case, still the copper is carrying, still carrying the platform here. But if we're going to extend the deformation of aluminum so that it will be inserted here, okay, so this is delta aluminum, then this temperature deformation will be up to that level so that it will begin to push the platform. Okay, so this is delta T aluminum. Okay, so let us have a recap on this. So if this is the original platform and this will be the final position of the platform, so the central rod will be placed in a way that it it will be inserted into this platform. So the indication of this insertion is that the central rod begins to push this upwards, so that the aluminum rod will be the only rod to carry this platform. Okay, and then for the two rods attached outside, it will also elongate by temperature. Okay, but it is exactly attached on the platform. So unlike on the first example, while this is pushing this platform, these two rods are being stretched. So in this case, the push caused by the central or the aluminum rod will not cause any stretch in the copper rod. So therefore, we're just have to label this to build delta temperature of the copper, and from here up to this point, this is delta T due to aluminum. Okay, and let us not disregard the gap here, 0.18, and this one is actually the delta of aluminum. So if you notice, there will be no delta for copper. So that is the condition wherein we will just have to elongate copper in terms of temperature, but not any stretch or any push on this platform. Okay, unlike the first problem, as I have said, while this is pushing this platform, it also stretches the copper, but this time this aluminum will just push the platform exactly where the deformation due to temperature of the copper will be exact on the same level. So this is our configuration on that deformation. So writing now our equation, so we'll just have to identify our reference, say this is our upper level and this will be the lower level. So I'll just have to get this dimension. Okay, and that dimension is delta T Cu actually, and equating it to this other variable, this is equal to delta T aluminum minus delta aluminum. Okay, minus 0.18. Okay, so what can we get from this equation? So let us have the formulas inserted. Alpha L delta T of the copper. This is alpha L delta T of the aluminum less PL all over AE of the aluminum less 0.18. So alpha for copper is equal to, for copper we have I'll just carry this one. Okay, so we'll carry it in here that we can see. Okay, so alpha for copper is 16.8 times 10 raised to negative 6. The length for copper is 750. Delta T, the initial delta is 10 degrees Celsius. But we are after with the final temperature, so do not adapt what is in the problem because that was already modified, wherein we are after now with the final temperature. We're going to less here the initial temperature of 10 degrees Celsius. So further, alpha of the aluminum is 23.1 times 10 raised to negative 6. The length is 750. We're going to deduct the short gap minus 0.18. Delta T is final temperature less the initial 10 degrees Celsius minus, okay, what is our P of aluminum here? So if ever that aluminum will just be stretched here or will just be stressed here, therefore it will carry, it will all carry the loading. Okay, so the loading is 100 kilograms multiplied by 9.81 times the length of aluminum is 750 less 0.18 all over the area. So the given area for aluminum, we have 400 millimeters squared with 70 gigapascal. 400, and this is 70,000 megapascal. So if you notice now, we have a single unknown final temperature, so that there will be no stress in the copper rod. So in short, the central rod will just carry all of the loading. Okay, and for our convenience, let us simplify this to be equal to 0.026262. So we have 15.55 degrees Celsius. So this is the final temperature, so that there will be no stress on the outer rods, particularly the copper rods on the sides of this platform, if our mass is equal to 100 kilogram for the platform. Okay, so that's it for the problem. So let me reiterate again that for problems in thermal stresses, we'll just have to relate to the geometry of the final position and the initial position, and then supplement it by equilibrium equation. So in this case, we do not have any stress on the outer rods. Okay, so please stand by for the next video on torsion, or on our next topic, particularly on torsion. Okay, thank you.